Hey everyone, welcome back. I trust you enjoyed your long holiday weekend. Let's continue on now with our last biochem chapter, which is going to be on carbohydrates, the big kahuna. I say that because I feel like I try to present the biochem chapters in order from the class of biomolecules that I'll have the least to say about, which for us was nucleic acids, as though they're unimportant. And then I work my way up gradually to carbohydrates, about which I'll have the most to say. And that's because there's a lot of chemistry here that we've already seen before. And it'll be nice to see that in action, see it actually applied. And there's a lot of structural details of carbohydrates that I think are going to be helpful background for those of you going on in biochemistry or upper level biology classes. Whereas, as I always say, these are going to be exactly the things they won't discuss in those classes. But I think it will be helpful structural background for those of you going on in those classes. So carbohydrates, I don't think I need to spend a lot of time convincing you about their importance. We understand carbohydrates as being one of the main sources of fuel for life as we understand it. We're going to start small with the smallest possible compounds that can really be considered to be carbohydrates, and then work our way up gradually to glucose. So that's what I have planned for this video. But in terms of structure, carbohydrates are polyhydroxyaldehydes and polyhydroxyketones, period, full stop. And we've recently done chapters on aldehydes and ketones, so we know a lot about how they behave. And last term in chapter 17, we covered alcohols, so we know a lot about how OH groups behave as well. The reason carbohydrates were called that is because they tend to have a formula somewhat close to CnH2nON. Maybe not exactly that, but something close to that. And it's almost as if it were CnH2ON. Of course, we understand structure well enough by now. We know that you don't make carbohydrates by taking carbons and literally sticking waters on them. That's not how this works. But they will have a formula equal to or near that one. So glucose is C6H12O6, as are a lot of other sugars, 8 common ones to be exact. And so you'll see that's like 6 carbons and 6 waters. Sucrose, table sugar, is C12H22O11, so it's 12 carbons and only 11 waters. It's close, pretty close to the same number of carbons as water molecules, so to speak. Now, let's, as I said, start with the smallest compounds that really are sugars at all, and the smallest possible ones have 3 carbons. Now, I know that we've seen this kind of structure before, probably way back in chapter 5, when we started talking about stereochemistry, and we discussed the differences between the type of stereoisomers, so enantiomers and diastereomers. We covered drawing structures in this way. There's a further shorthand to this kind of structure known as a Fischer projection. And so what I've drawn here is equivalent to this structure over here. Couple things about correctly drawing Fischer projections. First of all, we will just always assume that all horizontal bonds are going to be sticking out of the plane at us, and all vertical bonds will be going back into the plane. So these two structures are equivalent. They're showing the same information. Couple other caveats here. First of all, please do notice that in order to draw a correct Fischer projection, you cannot put a letter C at the intersection. Once you do that, it's no longer a Fischer projection. It's a perfectly fine structure, but it's just a flat structure and it does not convey any stereochemical information. So you must not put letter C's at the intersections. It's a common mistake that I've seen over the years. So please bear that in mind. In contrast with this type of structure, of course, it doesn't matter if we put a letter C there or not. it conveys the same information. But we're very picky with Fischer projections, and it is not a Fischer projection unless we let that intersection just be an intersection. Couple other things about Fischer projections. When you see Fischer projections in your biology or biochem textbooks, I think they will often leave out the H's and just put like a stick there. I'm not a fan of that. Let's not do that way. To me, it's confusing. I'm not sure then if they mean a methyl group. So at least for this class, let's draw all the H's in explicitly. And one other thing, when OHs go on the left side of the molecule like this, please write HO. Please don't write OH. It makes it look as though you're not aware that that the oxygen is connected to the carbon. And yeah, we are less picky about abbreviating groups like aldehyde functional groups here or CH2OH. We're less picky with carbon because carbon is 4 bonds, and so we have to make some concessions in order to keep things linear. But oxygen only is 2 bonds, so we can afford to be much pickier with oxygen. So please, please, always be sure you're making it clear where the attachment to oxygen is. So first thing to get down about the simplest sugars is really only 2 of them. One of them exists as a pair of enantiomers, and the other one is not chiral. The achiral one is dihydroxyacetone, or 1,3-dihydroxyacetone. You'll have heard of that in your biology classes, I think. It's generally abbreviated DHAP. And so I will be asking you to memorize these 3 simplest sugars. After that, it's only going to be glucose, just so you know. I don't think you even really have to work at memorizing dihydroxyacetone. Even if you say dihydroxyacetone instead of 1,3-dihydroxyacetone, there's only one way to put that molecule together that it all makes sense, right? You can't put the 2 OHs in the same carbon because that's a hydrate. That's not stable. That will lose water. So 1,3-dihydroxyacetone is the only sensible way to put those functional groups together. And so this molecule is not chiral. But glyceraldehyde has 2 possible forms. So as it turns out, D-glyceraldehyde is the R enantiomer, L-glyceraldehyde is the S enantiomer. I don't really care if you memorize that, but in case you're curious how the 2 relate. But the D and L system of naming compounds is commonplace in biochemistry. And what the D means is that the next to last or penultimate OH group, in which there's only one here, there's only one OH in a chiral carbon. But in the D enantiomer, that OH group will be on the right of the Fischer projection, if we always draw the Fischer projection with the convention of starting with the carbonyl group as nearest to the top as we can possibly get it. So we'll put the aldehyde group with its carbonyl at the top. So the D isomer will have the OH group pointing to the right, the L isomer, the OH pointing to the left. And so, so it's important to know D-glyceraldehyde and L-glyceraldehyde so you can recognize D and L sugars later on. And we'll go through that in just a moment. Another interesting and somewhat maddening coincidence here. Unfortunately, whereas it was the L amino acids that were natural, it's the D sugars that are natural. I do not know why. It's irritating, but it's the way it is. So D-glyceraldehyde is the type of glyceraldehyde that occurs naturally in living systems. L-glyceraldehyde is a thing. It most certainly exists. It's just not natural. It needs to be synthesized apart from living systems. So those are the 3 simplest sugars. And again, you want to look at the OH next to the bottom, the one that's just above the CH2OH group. I think you'll find there will always be a CH2OH group at the bottom. So it's the first chiral carbon above that last achiral carbon. That's what determines whether you're looking at a D sugar or an L sugar. So just to give some examples here, this compound, which I just made up, has 5 carbons total, 1, 2, 3, 4, 5. So that would be a pentose, whereas these 2 are trioses, actually. That would be also. And we identify it as being a D sugar because of that penultimate OH. Penultimate is just this $60 word meaning next to last. And so that makes it a D sugar. And we would identify this as an aldose because it is an aldehyde functional group in it. And so all told, this would be a D-aldopentose. So you can see how that breaks down. And I have no idea what that compound is, but I know it's a D sugar. I certainly would expect you to know that as well. I know that it's an aldose because it is an aldehyde functional group. And it's also a pentose because it is 5 carbons total. What about a ketose versus an aldose? Well, dihydroxyacetone is a ketose. A typical ketose will have the ketone carbon at position 2. So the ketone will be at carbon 2, and you'll get another CH2OH for carbon 1 at the top. This particular one is an L sugar because, again, that all-important penultimate OH group is now pointing to the left. And we would say this is a tetrose because there's, wait a minute, 1, 2, 3, 4, 5. I guess that's an L-ketopentose. I apologize. We'll fix that up straight away. A tetrose would have 4 carbons. But this is a pentose. It is 5 carbons. I think I meant to make a tetrose, but just forgot to remove another carbon. So anyway, that's one of the ways. Those are the ways in which we break down these structures and are able to classify them. There are other derivatives of sugars. You've got amino sugars, which involve replacing any of the OH groups with an amino group, NH2. We've also already seen deoxysugars, like deoxyribose. We talked about that in the nucleic acids chapter, and those are in which we replace any of the OH groups with a hydrogen. That's a deoxysugar. So all of these are other ways of classifying all of these things. Now, so like I said, I don't really care if you memorize any tetroses or pentoses. These 3 trioses, I think, are very important. If you memorize the structures of D and L glyceraldehyde, you get the definition of D and L along with it, and dihydroxyacetone is trivial, and all 3 of these molecules are important in biochemical pathways. It's a shame we're not doing chapter 29 because we'd see all of them in chapter 29. So like I said, if possible, if I'm able to do it, I'll put some lectures up on chapter 29, but you will never be responsible for it in the spring 2020 term. It will not appear on any hour exams or on the final exam. But in case some of you are interested, we'll try to get that done. Good, so the next important compound is, of course, glucose, namely D-glucose. And I am going to be expecting you to memorize the structure of D-glucose. And the way I always do it is right, left, right with the 4 OH groups. That's just my method of doing it. So, of course, carbons 1 and 6 are not chiral. The carbon 1 is the aldehyde carbon, and so that's sp2 hybridized, not chiral. And obviously, carbon 6 is not chiral. So the 4 chiral carbons in a row are right, left, right. And it's that last one to the right that makes this D-glucose. In order to get L-glucose, which certainly exists, you would need to flip the stereochemistry on all 4 of these carbons. So instead of right, left, right, L-glucose would be left, left. It's the enantiomer of D-glucose. What if you leave some of these the same and others different? Well, then you'll get another sugar. It'll be a different aldohexose. Now, if we're being careful to keep the OH and carbon 5 pointing to the right so that we're always dealing with natural sugars, with D sugars, you'll see that leaves us 3 other chiral carbons to play with. And if you work that out, there's 2 possibilities here, 2 possibilities here, 2 possibilities here. It's 2 cubed, or 2 times 2 times 2. There's 8 possibilities. And so there are 8 possible D-aldohexoses, of which D-glucose is one of them. You do not, repeat, not have to memorize the other 7 D-aldohexoses. Those of you going on to biochem will probably have that pleasure. For my class, you will not. Because for my money, if you have the structure of D-glucose memorized, then in principle, you know the structure of all of the other 7 D-aldohexoses. For example, if I were to tell you to draw galactose, given that galactose is just like glucose except at carbon 4, where it has the opposite configuration, well, that's trivial. You just switch the H and the OH. So we'll put our OH over here and our hydrogen over here. Presto, that's D-galactose. So that's why, as far as I'm concerned, if you know glucose in principle, you know all the other 7 as well. So let's memorize glucose, but not the other 7. If you, I would expect you to be able to draw any of the other 7 given enough information, given how they differ from glucose. And you can look at the old exam to see some ways in which I phrased that. As always, I would caution you not to get too focused on the phrasing or the format. It's understanding the idea regardless of how it's phrased. Good. So those are D-glucose and its other 7 friends, the other 7 D-aldohexoses. Now, this is only one form that D-glucose takes in aqueous solution, this straight chain form. There are a multitude of other forms that it also takes, and all of them are in a rapid mobile equilibrium. And yes, if you wanted to, you could look up at a certain temperature, at a certain concentration of glucose, what the relative concentration of the different forms are. But basically, this compound is going to form 5 or 6 membered cyclic hemiacetals. And we talked about acetals and hemiacetals in chapter 19. So please do review that. You're going to be responsible still for knowing those reactions, knowing their mechanisms, etc. And so, 2 of these cyclic hemiacetals are called the pyranose forms. And here I'm drawing them using what are known as Haworth projections, not to be confused with Fischer projections. But Haworth projections draw the 6-membered ring as though it were flat. Of course it isn't. So the bond angles are all wonky. But what we do get from the Haworth projections is that it's very easy to see which groups are pointing up and which groups are pointing down. That's very easy, much easier than it would be on a chair form. The reason these are called pyranoses is because they're related to pyran. Pyran is the parent molecule here. And so there are 2 different diastereomers, or anomers as they're also called, that are called the beta and alpha anomers. And I have trouble remembering which is which. The way I do it, and I have no doubt that you will find a better way to remember, but the way I manage to remember is that the vowels and consonants don't go together. So when the OH group is up, that's the beta anomer, because B and U are, it's a vowel and a consonant. They don't go together. Similarly, when the OH is down, that's the alpha anomer. So the vowels and consonants do not correspond. That's how I remember it. Like I said, I'm sure you'll come up with a better way. Now, the rest of this business here, I do not wish to spend time in this video on, because I must confess, I think it's a defect in me. No, I'm serious. I think it's a defect in me, to be honest. I find this whole question utterly boring, and I find no interest in it whatsoever. But I've observed over the last decade or so that a certain significant percentage of the students cannot move forward until I prove to them that you can get from this straight chain form to these pyranoses. And so that's what I've done here. I've taken you through that step by step. I've redrawn all of the carbons here, and I've shown you which bond to rotate around. I will tell you that as far as I can tell, so we tip the molecule this way for starters, and I'm taking you through that here. I will tell you that as far as I can tell, I can't find any necessary relationship between left and right here and up and down on this structure. Now, some students have told me that they've cracked that code. Again, I just find the whole thing utterly boring. And so I apologize. Again, I think it's a defect in my thinking. Maybe I'm just too willing to believe that these are the pyranose forms that correspond to this straight chain form, but that's the way it is. So for those who are interested, I'm taking you through this step by step to prove to you that we get these particular pyranose forms from that straight chain form. So you've got the straight chain form, and you've got these 2 pyranoses, alpha and beta. They come from the OH and carbon 5 attacking carbon 1, the carbonyl carbon. That part I find interesting. Exactly how it bends around makes my head hurt. I just have never been very interested in it. But some of you will be, and so I've provided this. But that's not the only way we can get a hemiacetal. We can also get not a six-membered, or not six-membered cyclic hemiacetals, but five-membered cyclic acetals. And those are called the furanose forms. I will not ask you to memorize these. I'm just giving them here because they'll show up in your biology and biochemistry classes. So they're called furanoses. You're familiar with furan, and these molecules are built on furan. Furan is the parent compound. And I did the same thing here. I showed you how to get step-by-step from the straight chain form to these furanose forms. So you will need to be able to draw either the straight chain form of glucose or the two pyranose forms in both Haworth projections and, get ready to go back to cyclohexanes, also in their chair forms. So it's a good review of cyclohexane conformations, because it turns out that you can also draw these using shapes of cyclohexane chairs. We're just replacing one of the CH2s with oxygen. And this turns out to be, in some ways, a convenient way to draw glucose as well. So I will expect you to know how to draw glucose in the open chain form, as well as the three carbon sugars, how to draw it in the two pyranose forms using the Haworth projections, and also how to draw the two pyranose forms using chair forms, like you see here. And so, like I said, this also turns out to be a convenient way to draw them as well. And I'll be honest, I have never memorized the Haworth projections. If I ever need to draw a Haworth projection, I just draw the chair form first, and I get it from the chair form. Why? Well, actually, before I get into that exciting bit, I do need to point out that your chair needs to be exactly that shape. It has to be this particular shape, not the other one, and the oxygen has to be back here for it to be correct. And so once you do that, the anomeric carbon, carbon 1, the carbon that used to be the aldehyde carbonyl carbon, is over here in front, just like it is in the Haworth projection, right? There's carbon, there's carbon 1 in the Haworth projection of the pyranose form, and so carbon 1 is over here in the chair form. So it does have to be this exact shape, or it will be wrong. What's the payoff? The payoff is quite considerable. It is very easy to memorize glucose in the chair form, because apart from the anomeric OH, which can be either up or down, right? If it's up, then it's beta, and if it's down, then it's alpha. All of the other non-hydrogen substituents in both cases are equatorial. I don't know why that is. I think it's just a coincidence, but it's a very useful coincidence and makes it real easy to memorize the structure of glucose in the chair form, provided that you're aware that the chair has to be this exact shape and that exact position relative to the viewer's eye, as opposed to any others. So I can leave you to read about the anomeric effect. I'm not sure I believe in it, and there are a lot of people much smarter than me who also don't believe in it, and a lot of people who are much smarter than me who do believe in it. So it's very hotly contested. And I've covered here what it is you will need to be able to draw, what it is you will need to memorize, and we've already covered ketoses versus aldoses, etc., along with amino sugars and deoxy sugars. So I think right there is a good place for us to end. We'll get into the reactions of simple sugars in the next video. Until then, stay well.